All right, good morning. Let's get started. We are entering week number 4. Not too many announcements here. As always, now the programming assignment is due. Someone asked where to find the programming assignment. I put it here in this. This is the big magical section table, so to speak. Homework, quizzes, and programming assignments all in one table. And there is the PDF for the programming assignment. It's due 2 weeks from now. So how's it going? Everybody's, some people I'm sure have, I think from office hour, have finished the programming assignment somehow, right? Have all of you at least started? Or maybe some of you are so comfortable you can do it at the end. If you haven't programmed a lot before, I would seriously consider starting right about this week. Because it takes time to debug. When it's breaking, me and the GSIs, we can kind of help you a little bit, but you got to learn the skill to find the bug, debugging code. If there are a systematic way to do it, it takes a lot of time. So even if the end result looks very short when you get it right, coming to that point can be quite difficult. You don't have too big, I think, programming problem set assignments. I told you what I feel about the problems in the book, that I assign 1 on each, so you get to use the method. Many people ask, what will the exams look like? And I think one answer is kind of like the examples I choose on the blackboard, because I don't have a calculator on the blackboard either. But you'll see, when the exam comes, I'll be posting a lot of, or several old exams, so you can see what type of problems we create. We are here now. I didn't quite finish this, but it's quite easy. I'll go through that. So you see that we're finished up all of chapter 2 now, which was solving equations, right? Root finding, or solving fx equals 0, or maybe gp equals p. We learned that was about the same thing. We're today going to start on chapter 3. The theme of that is, you can almost tell from the words in these sections here, it's interpolation. Namely, you have a function and you want to interpolate it through pointer. We have some data. So it's going pretty quickly here. Let me go back to chapter 2, though, and repeat what we said last time. We're done with Newton and analyzing it. You're doing homework on it, and that's all good. We talked about the variance of Newton for multiple roots, and you've looked into all that. Now, just at the end of chapter 2, there are a few things on... And Aitken actually had to do as well. I'm just repeating the fact that Aitken is not a method for solving roots. It's not like there's Newton, there's fixed point, there's Aitken, right? What is Aitken? Aitken takes a linear sequence and turns it, hopefully, into something better, okay? Which means that Aitken is not a method for doing anything like solving fx equals 0. What is Aitken? Aitken has to be used together with a linearly convergent sequence, like all those fixed point iterations we did in the beginning before we learned how to do it well. Okay? So is this worth doing when we have Newton? Maybe, maybe not. But for whatever reason, if you have something linear converging, you can speed it up with Aitken. Notation, this will come back a lot. Just get used to it. The delta notation, it's quite convenient. If you apply a delta on a sequence, or on an item in a sequence, it means that you take the next one minus the current one. And the cool thing, so that's easy, right? Nobody will have any problem with that. But the cool thing is that you can keep on doing it and get something that corresponds to higher order derivatives, but on a discrete sense, so higher order differences. So the second difference here would be to just do the same thing twice. And you showed on the blackboard last time that if you do this twice, of course you're getting a Pn plus 1, n plus 2, but then you're getting minus 2 of Pn plus 1 and plus Pn. So that's an example down here. And you can keep on going. So you will see more of that later. And the only reason we'll do it now is to write Aitken, because up here it's easy to mess up the n plus 1s and p's and stuff, right? Or maybe not. But if you really see this as a difference between two adjacent ones, and this as a second difference, then it's easier to remember. And by the way, there should be an n there, I see now. Okay? So this form might be easier to remember. It's really a difference squared divided by a second difference. Just notation. What can be said? We won't focus. I didn't prove this. We didn't look at it too much. It's a sort of vague statement saying that Aitken does improve the convergence, but not necessarily saying how much it improves it. Not necessarily that it turns it into quadratic. Stephenson was this idea of applying I know it's confusing, but the notation is just horrible here. It's so much easier. Actually, the MATLAB code is the easiest on the next page, but it's really just easy. You compute 3 numbers, you do a step of Aitken, you forget everything and take that result and repeat. That's what I'm saying. The notation here comes from the fact that I want to have a 0, 1, 2 because I have 3 steps of Aitken, right? So subscript 0, 1, 2 is always going to be there indicating the 3 steps that you then eventually do Aitken on, right? But then I need to say if I'm doing the first time, the second time. In math, in the computer, I don't have to do this. You know how I don't store everything when I do computer programs, but in the math notation, we have to say that this is the first time. But then the next time we do it, we're going to call it P1, okay? So you're going to have 3 times a lot of numbers, namely P0, P1, P2 for superscript 0, superscript 1, parentheses 1, etc., right? And the method is very simple. It really says start with a P0, 0. Compute 2 steps of fixed point, do an Aitken. Okay, this we now call our new P01, and you keep on going. So that's what the notation means. Looking at the coding, as I said, then you can forget all the history. It seems here that I call the 3 numbers P0, P1, P2 without any more details. So P0 comes in to this function, and you compute a P1 and P2 by 2 fixed point iterations. Then you do a step of Aitken on that, and for some reason I call that P. You could almost do P0 equals to here, because that's my plan, remember, to keep on going. And the only reason I don't do it is that I want to know if P minus P0 is so close that I can quit. But immediately after that, I say P0 equals P. So, you know, computer programs can be a little tricky, but this I think, really easily describes the logic behind Stephenson. It's a good method. And there's a theorem here saying that it can be quite good. And I mentioned last time that I do know that it's not used a lot. And I am actually not that sure why. And I think it has to do with the multidimensional generalization that it's not so easy as it is with Newton's method, which is 128b material. All right. So that was 2.5. In 2.6, we start focusing on one particular set of functions. I told you before that we focused on almost any functions. We require that they are smooth enough, so they are differentiable of some certain order. Like Newton required them to be twice differentiable. But if you know something about your function, it should be easier. Let's say you know that it's a straight line. Then you would probably not even apply Newton in the first place. You would just write down the solution. But let's say it's a quadratic. Well, you would probably not even think of numerical methods, because you have the quadratic formula, right? So if it is a cubic, what would you do? Maybe some of you would start looking, because there are closed form expressions for cubics and quartics, but they're actually not so convenient. So at that point, people start looking into numerical methods. But how about polynomials in general? It's a very important class of functions. They show up all the time, and I'm sure people want to compute the roots to polynomials. Now, knowing that it's a polynomial, we should be able to do some smart things. And one smart thing, of course, you can just run Newton on the polynomial and be happy. But let me tell you one thing that's going to happen. Here's a general problem. It's not just polynomials. You can imagine that the user would like to have a function called find all the zeros of this function. And we mentioned a few things with Newton. One problem was, let me list the problems with Newton. One is that you need the derivative. Okay, we haven't suffered from that much, but you need the derivative. The other is that it had a 0 derivative at the root. That was a problem, remember? But we could fix it. We had a modified Newton. I think the biggest problem is that delta. How do we know if it's even going to converge to anything, right? You got to start. You need a good initial guess. That's how people often summarize Newton. Okay? So suppose then I have a function with many roots, like this, right? And it could be a polynomial, but let's say it doesn't really matter. How do you run Newton on this? Do you draw it first? And many of you asked for the problem set, how do we start? How do we know what to do here? And the answer is you don't. And maybe we should give you even more practice to show you just don't know where to start. Maybe you know something from before. Maybe for physical reasons, you know that this is 5 micrometer or something, right? Because it can't be closer than this to whatever. So there are sometimes people have some argument. So if you start here, I think you can all see that Newton is going to nail this guy. If you start here, Newton is going to run far away. If you start here, it's going to get this guy, etc., right? Can you write a computer code that finds them all? Can you think of some logic for doing that? I mean, it's just thinking a little stupid here. Why don't we just run it once and see if we find one? If it breaks, we catches that and start over or something. But if we have one, we could go a little bit to the left and try again and systematically try to see. You can have all these ideas. What you're doing in the programming assignment number 1 is a little bit in this direction, that you try to bound things. But remember, it's based on the bisection idea. You don't really know how many you have in there. Bisection doesn't solve this problem either. It only tells you that there's a root, and you can miss roots. So how do you get them all? Well, what I'm trying to come at here, yeah, it's a suggestion.
Look where the second derivative equals 0 and take that as your starting point.
Second derivative equals 0. And that would be a new starting point?
That seems like where all the lines.
That's the inflection point. That's the turning point of the curve. Yeah, I'm sure that could be an idea. But then you would probably not appreciate this, right? Because you would start a lot of starting points here. And you would fly far away because there are no roots. So, and there are lots of second derivatives here. You really want to find these guys, right? So, look, I'm not saying there's not something you can do. I'm sure there's a lot. But the point is that the one big thing we could do with polynomials is find them all. Because we know it's a polynomial. We know stuff about polynomials. So that's part of the machinery we're going to develop here. Namely, the idea of how do you find all of them. And so just to point it out, it's actually very simple. Suppose you find one, let's say with Newton. Let's say you just start somewhere. In fact, starting really high on a polynomial, since they all go to infinity or minus infinity, except the constants, it's kind of easy to find one. That's actually the good news. You could argue that you don't want to do a too bad initial guess, but finding one is quite easy. But systematically finding all of them by just keep on guessing initial guesses is difficult. You could probably argue that starting very far here would lead you to the leftmost one unless you're unlucky or something, right? But then what? Here's kind of great news about polynomials, long division. And we did it in calculus a lot. If I find a root, let's say x0 here, I could just divide out a factor x minus x0, right? And the result is a new polynomial of 1 less degree that doesn't have that at a root. So maybe that polynomial looks like this, right? But it doesn't have that at a root, so then you keep on going. That's kind of the end result of one of the techniques we're going to discuss here. But anyway, it's also a chapter that summarizes polynomial in a more broader sense. You've seen all these results. I'll quickly repeat them. A polynomial, what is a polynomial? You need to know that. But there it is. We like to write the coefficient such that a subindex matches the power there. But we will violate that when we do strange things like derivatives. You know that algebra tells you the thing I kind of just told you, that first of all polynomials have a root, but unfortunately you might have to go complex. If you find one root, you can divide it out. Or sorry, you can divide out a factor x minus that root, right? And if you keep on going, eventually you're down to the constant. And that can be summarized as this corollary here, that any polynomial can be written as some leading coefficient times a bunch of x minus roots to some power or some multiplicity. Okay? So these are how polynomials work. So finding all the roots is really a question of finding these x1, x2, all the way up to xk. I'm not calling the k n, right? There are not n roots necessarily. There are n roots including multiplicities, which is expressed here. But there could be just one root with a lot of multiplicity. And a perfect example of that is x to the 5, which has a root at 0 of multiplicity 5. Here's a nice corollary that I think you all knew as well. Namely, if you have two polynomials that are degree n or less, and they agree at more than n points, they are the same polynomials. It sounds maybe surprising, but it shouldn't be. I told you last time, if you have 2 points, you know you can draw a straight line between them. All I'm saying now is that there's only one straight line going between them. So if you give me 2 points, or so another way to say this is like this. If you have two polynomials that are degree 1, and you say, oh, they're equal at these 2 points. Well, they have to be the straight line going through those points. And bring this further up, 3 points. It has to be one unique parabola. We will use that more later. Here's Horner's method that you may or may not have seen. It's just a very efficient method to evaluate polynomials. But it turns out it does more. It also divides out those factors. Okay? So it's kind of doing what you would do with long division. I actually don't know operation-wise but I know this one is really implemented in a lot of software. So I'm sure this is close to the optimal of what you can do. I discussed last time that evaluating something like a long polynomial can be done in a naive way by just starting from the left. You would probably start from the right, but let's say you start from the left, you would say x to the n, well, let's take x times x times x n times, right? And then times a n, and then we keep on going. And I mentioned that's obviously not optimal, because if you do it from the other way, you can just have this x to the n minus 1 and just multiply that by x. You know, you can organize this in a way so you can do it smarter. But one way to organize it is this. And by the way, this is very similar. I think someone mentioned a term in office hours, synthetic division. Very similar. Ideas just to evaluate these fast. But this is called Horner's method. We will use it because it also factorizes it for us. So here's the theorem. You take a polynomial, and you just follow this formula, namely say that b, the highest one, is equal to the highest one. So here, in my little example here, I just said that the highest one, phi, I have a little polynomial, 1 times x5 minus 2x4 plus 3x3 minus 4x2 plus 1 times x minus 2. Okay? I just made that up. You write the coefficients like this, and you apply that formula on the b's that says that the highest one is really just equal, and all the other ones come from having an evaluation point, in my example, minus 1, a little too easy to, maybe I should have done 2, but I want to keep the numbers bounded here. So basically what you just do is that you take that, a4, and then you do, the formula tells you plus the higher b times your evaluation point. So in my case, minus 2 plus 1 times minus 1. So that's minus 3. b3 is 3 plus minus 3 times minus 1, which is plus 3, which is 6. b2 is minus 4, and it ends up being minus 6, so it's minus 10. b1 is 1 minus minus 10, which is 11. And squeezing b0 here. They should really be below each other, so you see the pattern. But that would be 2 plus 11 times minus 1, which is minus. So this is minus 9, OK? So you have a bunch of numbers here. And let's see what we do with these numbers. First of all, the theorem immediately tells you that you're done if all you wanted to do was evaluate. So that's one application of Horner, to just quickly and an easy way evaluate pretty long and messy polynomials without having to do the x to the 5 and everything. But it does more. It also tells you that p of x can, as I mentioned, we factored out x minus x0. Whether or not x0 is a root, of course, minus 1 is not a root. How do I know it's not a root? This is not 0, right? I just evaluated the polynomial at x0. And I told you this was that value. So if this is 0, that's good news. Then it was a root. If that's good news to you, whatever. It depends on what you want to do. But regardless, it tells you that you did find a q, namely these b coefficients, except the last one, that is the factor that you get out when you divide by x minus x0. And there's a remainder, which is that minus 9. So it means that we can write this whole polynomial. Knowing this, we can write p of x as x minus minus 1, x minus x0, times q, where the q is really equal to this, but 1 degree lower. So let's see. Let me write it down and see. Plus 6x squared minus 10x plus 11, and parentheses, right? And then we got to have the b0 as well, which simply says minus 9. So sorry about the mess here, but you can see here that this is what I mentioned, that sometimes we won't match the subscript on the coefficient with the power there because it's 1 degree lower, and this bn makes more sense. So it is what it is. But it's really 1 degree lower, and this is the factor we got out. And basically the main application of this, now you can find a lot of applications. Every time you want to divide out something, you get it for free from this. But the main application here is, of course, to do what I said over there, try to find a root, keep on doing this. If this one is small, what do? We just say, fine, that's a root, right? I don't want to get into the details of termination criteria. But one of the ones we used a lot was to look at f of x and see if it's close to 0, we're done, right? And you might want to combine it with something else. But let's say this is close to 0. Then that means that you divided out truly a root, and you can just grab this part, which is my second attempt there of saying, hey, it's 1 degree lower. And in principle, we should be able to keep on going, right? This is just a fourth. This is just a quartic, so you can now do the same there, and it becomes a cubic. And when do you stop? So you could stop at the quadratic, because you have a quadratic formula, so why not? That's actually kind of nice. or keep on going. Linear. At some point you have to stop, obviously. The constant, unless it's 0, has no roots. More details. You can get more. We can squeeze more out of Horner. If px is equal to x minus x0 q of x plus b0, what if you want the derivative? And why would I want the derivative in this whole setting? Newton wants the derivative, right? So can we easily just get the derivative out of this? Well, it turns out to be kind of nice. You could, of course, just differentiate and say 5x4 minus 8x3, etc., right? And apply. It's just a polynomial. But it comes almost easier out of this for free, because if you look at px, it's this linear factor times q plus a constant. So if you differentiate that, you really just get q plus the linear factor times the q prime. And what that means in particular is that if you plug in x0 in this expression here, you see that evaluating p, this term here dies, right? Kind of a nice trick. So p prime at this x0 is really just equal to the q at x0, which means that you take these coefficients that you just had and apply Horner again. Let me do it. I'm going to write it again, but you should probably write them next to each other. So then we get, I'm just going to sloppy, just write them like this, minus 3, 6, minus 10, and 11. That's a new polynomial, right? And it is the q polynomial here that we wrote out here. And we just showed that if you now want the derivative at that point, just do Horner on this quickly, which says 1 minus 3 minus 1, 6, that's 10, I guess, minus 10 minus 10. And here we get 11 minus, that's 31, right? So this is now the new B0 according to that old notation. But let's just say that it means that P prime evaluated at x0, which is 1, no, minus 1, is equal to this number, 31. All right? So a lot of benefits of the Horner's method. Things that you would have been able to do easily. Evaluate polynomial, differentiate polynomial, and even factoring out you would do by long division. It does it in one sweep with a short method, and it has its value. Let's look at my little computer code doing this. A little cryptic, actually, because I call things weird names like x and y. Yeah, question. So I messed up here. These should all be below each other, right? And so this one should really be there, OK? Right. So they're exactly the same number. Here's what's happened. The last number is really just the coefficient you evaluate. And the q itself was one fewer, right? So this is the q. And that's the evaluation. Suppose I wanted to keep on going here. Then this would be the evaluation. And this would be the next q, so to speak, if I wanted to keep on dividing. But yeah, so sorry. Write it in a table below each other nicely. This is bad. Look at this code. It's really doing exactly what I did on the blackboard, and you might want to see that it does. But the goal of this, the idea here is to really just plug it into Newton, and it's outputting. It's bad names. This is bad computer code. I'm not happy about it actually. I should rewrite it, but it's good. It forces you to think a little bit. Apparently, I take a. That sounds like those coefficients, and indeed, if you read the code, you'll see that it is. And by the way, have you worked with polynomials in MATLAB? If you get a vector of a, you have to wonder what is a5 and what is a0, right? And to begin with, there is no a of 0 in MATLAB because vectors start at 1. So you have that whole issue, right? And as another little, so one natural thing would be to say a parenthesis 1 is the first one, which would be this, etc. That would be a natural way to do it. Unfortunately, that's not how MATLAB decided to do it. They rather decided that when you write the vector from left to right, it's just like, you see, I wrote it starting from the highest one, and that's how you usually sort polynomials. So they decided that it's a vector of these numbers, exactly like I wrote them here. Okay? So that's just what it is, and that's what I'm using in this code as well. How could you figure that out? Well, you know that Horner starts by saying b of n is equal to a of n. Since I start by saying something involving a of 1, it sounds like I start from the left, from the highest terms there. But that's not a proof in any way. Anyway, look how simple this scheme is. I have a loop going through like I did. I do this little operation, the previous number times this evaluation point x, and I add in another coefficient, right? So it was that coefficient plus that times the x. And that just builds up this y. Even more, I'm throwing them all away. You see that? This is not what you want to do if you want the q at the end. Okay? But if you just want this minus 9 here, you can throw them all away. Kind of nice. You can write very efficient computer code. What if you want the derivative as well? You can still throw them all away if you do it on the fly. So the z's here is doing this procedure on the fly. I split it up. I first did this. I got these coefficients out. I copied them over here and did it again. You can all see that when I compute this first number I computed, the minus 3, I could immediately compute this minus 4 and then move on and forget about the rest. That's what this computer code is doing. So I encourage you to go through just to learn Horner how it works. It really tells you a lot of insight about the method. This, however, does not give you the actual q at the end because I throw them all away. If you want them, just store all those y's that I compute in another code, right? But here I'm not doing that. So this is a perfect little snippet of code to put in a Newton solver because it will give you p of some value x and p prime at that value x. You just divide them and keep on doing Newton, right? So it's quite convenient. Anyway, so much about Horner's method. Here's the method I said before. It's called deflation. The idea is the following. You compute an approximate root. Let's call it x1 hat. I'd like to call it x1, but that's really what we call roots. So let's just call it x1 hat to say that it's not perfect. So then p of x, but it can really be numerically in the computer pretty close, right? You can keep on going until this number is, let's say, 10 to the minus 10, and you would say, I'm fine. This is a root. But there are issues with that. Then you know that this is going to happen, or in other words, that the b0 is close to 0. So let's say this is the case, right? And I already gave away the idea here. Then you just take q1, and you accept this x1 hat as a root, and you continue with q1 until it's so low degree that you're done. Isn't that a nice technique? In fact, I wish, I guess I got stuck with too many programming assignments, but a great programming assignment would be to just do what I just said. Write a little Horner method, doing Newton. If it finds a root, it deflates and keeps on going. There are some nice while loops to do that, and you know, you would really get a function getting all these numbers out. How about the issue that, how bad do you think that this x hat of 1 is wrong? I mean, I don't want to go into too much of termination. How do you know that you're close enough? But in this setting, I'd like to point something out, that even if x1 is pretty close and you seem happy, you're making new errors that accumulate as you divide these out. So at the end, it can actually be quite bad. So let's just say that suppose that this guy here was not really, it's a little bit off, right? That means that the new polynomial, all of these guys will be a little bit off. And then in addition, you will compute them approximately and get them a little bit off. So things tend to accumulate. So the errors can be surprisingly high in the end when you have all those roots. What can you do? Well, it's my last line. But what if this method ends up really working, you're quite happy, but you just notice that, whoa, it's not that accurate. The first one you compute here was really 10 to the minus 8, like you said, and you were really happy. But suppose that these guys really drift away, and they are fine, but you know, you look at them, and they're like 10 to the minus 3 away, and the user wanted 10 to the minus 8. Then you just go back to forget everything about Horner. Well, Horner you want to keep, but forget all about the deflation. Go back to the original polynomial and just do 1 or 2 steps of Newton, right? And you will nail them back to where they should be without these accumulated errors. It's a nice trick. So as I said, this would be a really nice little programming assignment, but I didn't do it. I think at the very most, I had some homework problem where you do this by hand for next week. All right. One final thing in this chapter is something called Müller's method. It's really, it's quite messy expression. Frequently asked questions, do we need to memorize these expressions? And the answer is no, not really. But you need to know what the method is doing. So let me tell you what it does. It's really, I guess, similar to the secant method. But instead of doing a straight line, it puts a parabola. OK? So an ugly drawing here would be the following. You're trying to solve. So the whole deflation and everything is over. This is a new method for finding zeros. that is mentioned in this section on polynomials because it turns out to be widely used for polynomials. And there's actually a good reason for it. Let me show you. So here's a root, or many roots. Secant method took 2 points, evaluated at those 2 points, and drew a straight line. It looks very good the way I did it here, right? But maybe it's not that good always. And then it finds the root of that. Just generalizing this and saying, hey, how about something else? Why don't we have 3 points? And those 3 points could really be anything. But they could, for example, what if they look a little messy? You have these 3 points. Then you can put a parabola through those 3. And it would look like this, getting messy. And then you can compute the root of that instead of that. OK? Now, in my figure, it looks like it's worse, which it might be. But in general, it seems like as you get close to the root, if the function really is a parabola, this might be a good idea. So that's Miller's method. And you could actually, just based on what I just said, develop this whole method. That would be a nice exercise. It's a little messy, though, to just get the numbers out. And in the book, you'll see a whole page of expressions. I put them also in a code for you that you can use if you understand it. I call it Miller, just to show that the expressions are a little nasty. They kind of cleaned it up, but it's still surprisingly messy. Well, maybe not. I mean, these are quite short. They wrote it in a nice form. But what's big here is, of course, to realize what's being done, and that the algebra can be done if needed, and we have it. And also realize the properties of this method. One clear thing, there are a few good things to this. And one is that it has the potential. So one thing I haven't addressed too much is, go back to Newton. We said before that roots of polynomials might be complex, even if the coefficients are real. You think Newton, as we wrote it, would give you a complex root? So a typical scenario of a complex root would be if you have a polynomial doing this and then going away, and there is no root, right? Maybe you would say there is no root, but what you mean is there is no real root, because the fundamental theorem of algebra tells us there are exactly n roots if it's a degree n polynomial. It's just that they might be complex, right? So what will Newton do? Does Newton like these functions? You start here. Newton is actually known, infamous, for getting stuck in these. Well, it's clearly, when it gets down, it gets flatter and flatter, right? And then it's going to fly away. But in this case, it might actually bounce back and forth. It's just that. Okay? So it might stay in that little pit there, but it's not really going to get anything. Clearly, but here's what I'm trying to say. If you look at the expression, x minus fx over f prime of x, how could that possibly go complex if everything is real? It's just not going to decide to go complex in any way. Actually, if you start with an initial guess that is instead of 5 plus square root of minus 1, you might actually just move it into the beautiful world of complex numbers, and it might accidentally find it. So Newton really works with complex numbers. I mean, Taylor is nothing real, right? I mean, that's just, you can do all that with complex numbers. But if you start with real numbers, it might not. I think the punchline about this Miller method is that when you start putting parabola like this, when I mentioned that you find this root, of course, here, you will find another root over here, because it's a parabola. It's a quadratic, right? And those two might be complex. So that's the benefit of the method, that they might bring out these complex numbers. But let's just summarize what we say. Fit the quadratic polynomial through the 3 points that you have. What are the new 3 points? How exactly do you do this? You want to solve now this, and here they say, why don't you pick the one closest to P2? So in my case, I would pick the one I drew there. And then you shuffle things around, so now you use P1, P2, P3, just like the secant method. All right? This is best seen by a demo. I have this Miller plot here. So let's try this. It's just plotting. You might not want to read all that plotting thing. But it seems like I want all of this. All right? So here's a function. x4 minus x3 plus 3 times x2 minus 2. I have no idea about anything. So P0, P1, and P2, I'm going to do one. Well, I do because I tried it before. But 0, 1, 2 is a good initial guess, maybe, right? So f 0, 1, 2. How many times? Let's go for 8 iterations. And xmin and xmax I've had in my plotting functions before. It's just so I know what to plot. It has nothing to do with the method. But let's say we want to zoom in a little bit around this function like that. And this will now plot the function and plot 3 points. It goes a little too fast, so I'll run it twice. And then it will put a quadratic and grab that root. I meant Mueller plot. All right. So there are 3 points. Yeah, this goes way too fast. If it goes too fast, what do? You edit the file. You figure out where I slow it down. And you find a line called pause. And you just change that. In fact, make it pause without the number. You know what it will do? Any MATLAB experts here? Yeah. It will wait for me to press enter. Or you could change it to pause on 5 if you want to wait for 5 seconds. So let's run it again. Anyway, here we are. You know what? These dots, I would like to be much bigger. So let's do some more MATLAB thing here. Where am I plotting these? Here are my markers. Marker size. Marker size 16. OK. Now we're talking. Well, still not big enough. I want you guys to see this. All right. 3 points and a green line. This is the whole thing. You can see that I did choose really good points because there seemed to be a root between around 0.8 or something, right? And this guy is putting a green quadratic between those. You see that the green also has a negative root? I'm ditching it because the logic said pick the one closest to P2 for whatever reason. Now what? Well, the logic is keep P1, P2, and the new one. So it's actually going to throw away 0, which is a bad decision. But it doesn't know that. So those are the 3 new points. And the new root might not be all that much better. But at least now you know, just because I decided that 2 was my last point before, it's still going to be in the game. So maybe 0, 1, 2 was not initial guess. It's kind of complicated. Now it will, of course, throw away 2. Because now we have computed 3 new ones. These are the new. Now it's going to be really accurate. And I should probably zoom in to see that. But you can also look at the numbers in the table to see that it's getting there. Surprisingly slowly, though. But the next one should be. There we go with a little bit better convergence. So that's the whole method. Well, so not too interesting. The green line is like on top of the blue line. You can't even see the function. That's how accurate it is. Anyway, so it's kind of similar. It's not really Newton. It doesn't use derivatives. It's more like the secant method, right? What if I change the function to add 2 instead? Where is the root? Well, as you see, the blue line doesn't even seem to cross the 0, the x-axis, right? And indeed, my function starts complaining when I'm plotting. That's because I don't know how to plot this. Well, so it's a bad example. Let me run it without plotting. So you can't see it, right? So I'm trying to do this. So plotting doesn't make sense because it tries to find the root and it freaks out and everything goes complex. But let's just run the table version. You can see that it actually does converge and gives us a complex root such that f of p is close to 0 in a complex sense. Okay? So this is to exemplify the fact that it might just be nice to put quadratics because they will bring the method to the complex world if needed. But you could do that. But so that's one of the things that are often celebrated. Of course, the whole deflation, etc., could be used now on this. All right? That's about it. That's chapter 2. Any questions? Let's see how you like the problem sets on this. It's pretty straightforward, I think. They're meant to show these. You can see the importance of it. We take them all for granted. By the way, I mean, here's how granted we take these things. What was this? What was my example? It was f equals this, right? So in MATLAB, you would write this polynomial like this. No. OK? So I just told you in MATLAB, you write the coefficients starting from the highest. And for, do you see why I put a 0 there? Easy to make mistakes, right? But it's really a 0 times x. MATLAB needs to know. Otherwise, it would think it's a different polynomial. So there is, of course, a function in MATLAB giving you all these guys. OK? And you can wonder how it's implemented. And it could very well be the method we discussed. Turns out that when you learn about something called eigenvalues, there are even better methods to do this. And that's how they do it. It's good if you were to develop, if this was a programming assignment that you would be doing this, of course, you would be running this command all the time to check your answers. And it would be much faster than your code. But don't get depressed. All right. Next huge topic. We know how to solve equations. Now we're going to interpolate, in particular with polynomials, almost entirely with polynomials. It's going to lead up to something that you might have heard about that is called splines, which is really popular in all type of CAD and computer graphics. That's how all those, most of those fancy, anything computer generated you're watching are made up of surfaces that are not quite polynomials, but something called rational non-uniform functions. But it's not too different from that. So you might have heard the word spline, and that's often used to represent functions. And the idea is basically that there are a lot of functions, and we just don't know how to tell a computer what those functions are, so why don't we start approximating them by polynomials? We did this already with Taylor. Remember, I motivated Taylor, and you did some little silly example in the problem sets where we just said, hey, and it was like a little made up, but I think I said, suppose you have e to the x, and you want to evaluate it in the computer, and the computer doesn't know. E to the x is a very difficult function. And let's just say for now, you know that you're only going to evaluate it for x really small. Then we argued that, this P2, as we called it, which was the first Taylor the second-degree Taylor polynomial to that function, is a pretty good approximation close to 0, right? And then you had exercises where you had to look at the error bounds and actually guarantee that it would never be worse than something if it was close enough, etc., right? So this was, what was this? What did I just do? Well, it's actually not directly, it's almost interpolation in a generalized sense. I'm interpolating the function at this point. You could also argue I'm interpolating the derivatives. I actually found a function P2 that is quadratic polynomial that agrees with e to the x at this point, and it also agrees with its derivative and its second derivative. So it's kind of a generalized form of interpolation. But the way I think you see interpolation would be something else. I think you would think that I gave you several points, and you put the quadratic through those 3, right? And that's indeed the case we're going to start addressing. That's the typical traditional interpolation. But it's really doing kind of the same thing. It would give you a new quadratic that you actually probably would say might be better in this case, but it depends on what you want. But no matter what, you have a function, or actually just loose points, loose data, and you want to interpolate by a function in between. Huge field in almost any. Imagine a physicist going out and measuring stuff in some experiment and wanting to evaluate the points in between. How do you do that? Suppose you get this data from an experiment, and you're really interested in figuring out where the sweet spot of whatever is. How do you do that? Well, interpolation is the general term for all of this, right? You just fit something. You have to figure out something, whatever. We're going to start with polynomials. Now, you know how to do this. You actually know how to do these 3 things here. We just did it with Miller's method. How do you fit the parabola to 3 points? I think most of you, this is what I think most of you would do. Already in high school, you would write down what you want, namely a polynomial. I think you would say p of x is equal to ax squared plus bx plus c. Then I told you I want it to be equal to, I give you 3 points, and I tell you what it should be at those 3 points. And you would, for example, let's say, if you plug in 0, it should be equal to 1. If you plug in 1, it should be equal to -1. If you plug in 2, it should be equal to 3. what is the quadratic? What you would do is that you would say P of 0 in your form is A times 0 squared plus B times 0 plus C is actually just equal to C, right? And that has to be equal to 1. And then you would plug in 1, and you would get A plus B plus C equals minus 1. And then you would plug in 2, and then you would get 4A, and you get 2B, and you get a C, and that has to be equal to 3. Right? What is this? Chapter 6, a big part of this course, the very last thing we'll be doing, is solving linear systems of equations. And we'll look at things you didn't know before, but what I know you know now is to solve this. In particular, if I give you this easy thing. Because C is equal to 1 means that you kill it out from here, and you subtract 1 here, right? Give minus 2, 2. And then, unfortunately, you're going to have to do one step of elimination, right? But whatever you call it, you multiply both by 4 and subtract or something, right? And you get the coefficients out, and you're done. Is this nice or not? Certainly a common way of doing it. It has its role. There are some benefits. When you get these numbers out, they're like magic numbers, and it was a complicated procedure to get them. You don't really know what happens easily if I change this to 0.1 instead. You just don't see it. So just trust me for now that there are going to be cases when it would be nice if I could just write down, not A, B, C, but I could write down Px equals and just an expression. I could actually now and that, using the technique we'll learn, I can write P of x equals blah, 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 period, I'm done. Okay? And I'm not saying it's that much easier than this. It will be still a full blackboard of stuff, right? But at least there is no procedure involved that is implicit in the sense that you have to solve a linear system. And it has its role. But for now, just accept. I don't think they teach this in, we don't teach it in calculus, actually. It's called the Lagrange interpolant. So let's see where we can get with that. First, just some spirit building here about why polynomials are so amazing. Polynomials are often used for approximating functions or interpolating functions. Why? Well, polynomials are nice in many ways. They're really easy to evaluate. For example, that should be an n, by the way. They're really easy to evaluate using Horner's method or any method. Maybe even bigger reason that they're used is that they are really easy to do calculus with, in particular differentiation and integration. Suppose I decide to play, I mean, there are a lot of actually very famous interpolating functions used out there. I'm sure some of you have heard about FFTs and Fourier series. And that's doing the same thing, but with sine and cos instead. Okay? And they're actually also very easy to differentiate and integrate. So, you know, these are some of the motivations. Is a polynomial good to approximate the function? Is it reasonable to say that I want to approximate e to the x by a function that is a polynomial? I mean, what if I said that I want to approximate it by a Gaussian? Do you know what a Gaussian is? Something of the form e to the minus x squared, but with coefficients. You could argue that that's never going to be any good for approximating e to the x, right? It would be really good for approximating another Gaussian if you find the coefficients, right? And anything that looks kind of like a bump, it might be good. But it's not good for this, right? So I'm just saying some functions are just not good to interpolate. Sine, since the Fourier series. Do you think sine and cos would be good to approximate e to the x? It can be done. They're convergent, but it's not a periodic function, right? They are better at other things. So all that this bullet here is trying to say is that there is actually some theory saying that polynomials can be really, really good, in the sense that there is a polynomial that is arbitrarily close to f in some sort of epsilon that you have to choose. But you have to bring up the degree to make it better. But this is just saying that why we want to approximate by polynomials. Let's go straight to this little thing I mentioned, the Lagrange polynomial. Here's what it says. It's a big theorem. Let's just understand it. So you give me n plus, so just notation here. You're going to give me numbers, and let's call them x0, x1, and x2, okay? And in my example, it's minus 1, 0, and 1, okay? F at those points are the data that you want to interpolate. And you're looking for a polynomial such that at these 3 points, or in general n plus 1 points, at P and F, they agree. They're equal, right? The first statement of this theorem we already discussed before, and it's exactly what we said before, namely that there can only be one unique. This uniqueness came from that corollary before, that you have 2 polynomials agreeing on 3 points. On n plus 1 points, they are the same polynomials. Anyway, here comes the actual theorem here. Here's just the expression for this polynomial. Lagrange polynomials, it writes it out as each of these values, f of x0, f of x1, etc., times something called the Lagrange interpolating polynomials. And they look like a disaster here, but that's just because it's a general case. When I write it down, it's a little bit easier. All right? And we'll prove where this comes from. It's actually quite straightforward, but let's just look where it is. So it's really writing the polynomial as f of x, in this case, e to the minus 1, e to the 0, and e to the 1, right? Multiplying polynomials of degree 2, of course. And those polynomials look a little funky. They are products of these little factors here, x minus various xi's, and these are just numbers. These are not x's, right? It's not a rational function. It's just a polynomial. And you have to go through everything except the current term. So we define an L of n comma k. Let me draw a few of them. So these are the Lagrange interpolating polynomials. So what is one of these guys? Lagrange, let's just say polynomials. So what are these guys for example, n is equal to 0? Well, you have a point x0, and it seems like when n is equal to, it seems like we define a bunch of functions L of n comma k, and it's not explicitly spelled out, but you can see that this k can be 0, 1, 2, all the way up to n. So when n is, and it's going to be a polynomial of degree only going up to n. So let's start with n equals 0. Then you have 1 point. And what is this polynomial? Well, I could tell you what it should be, but let's look at this expression. It's really a product of i's not equal to 0, but it's only allowed to be 0. So it's not allowed to be anything. What is an empty product? Have you thought about that? This is like when they design things like MATLAB. So sum of 1 and 2 is 3, right? Sum of 1 is 1. What is sum of empty? 0, that's very reasonable. You have no items. You're trying to add up how much they are. They are 0. You think I'm crazy? Yes, fine. But here comes the point. What is the product of 1 and 3? 3, right? What is the product of 1? That's a bad example. Can I do 2 instead? Product of 2 and 12 and 3 is 36. Product of 12 is 12. What is the product of empty? Has to be 1. You see why? Because only reasonable, because we need to know that a product, is non-zero if you just multiply by positive and stuff like that. Or the algorithm could be set it to 1, keep on multiplying by everything. So this is what it does. So if you go back to this expression, L of 0, comma 0 is the product of all the i's that aren't 0, but they can't be more than 0, so there's nothing. So what is the polynomial? L of 0, comma 0 of x is equal to that 1, because there are no factors in that product. Anyway, don't worry about it too much. Here's another verbal description of these Lagrange interpolating points. You give me a bunch of points, in this case just 1 point. I'm going to find a polynomial of degree n plus, of degree n, sorry, that agrees with all these points. No, that is equal to 1 at the point where the k matches. So L0, comma 0 is really, in words, the 0th degree polynomial that is equal to 1 at point x0. Okay? There's only one such polynomial, and it's the 1. So this is a special case, so don't freak out too much about this case. The next one is better. N is equal to 1. Okay? So here you're going to have 2 points, x0 and x1. Okay? And now in words, the Lagrange polynomial, we're going to have 2 Lagrange polynomials, L of 1, 0, L of 0, 1, 1. Let's look at L of 1, 0. In words, it is the polynomial that is equal to 1 at the first point and 0 at all the other ones. Okay? Guess what? That nice little product at the bottom there is the expression. Namely, consider all the i's between 0 and 1 that are not equal to k equals 0. That's 1. So it's going to be x minus x1 divided by x0 minus x1. That is the polynomial. Not the end interpolating, but the one doing exactly this, right? Okay, you'll see later why we're doing this. But there's another one, of course, that we call L of 1, 1. And how do we define that? Well, it's the product over all i's that are not equal to k equals 1. So it's going to be x minus x0 divided by x1 minus x0. 2 straight lines. They seem kind of arbitrary. Why do I even make them up? But now let's use the middle line to see how you can interpolate using this. And for straight lines, it's so easy that you won't quite see the point, but it will get more complicated. So now suppose that you want to use this to find the interpolating line through the points 1, minus 2 and 3, 3. And of course, in high school, you would just use some little expression about the straight line or something. But let's just use the middle equation here. Now that we have these guys, it's really saying that px is really just equal to f at the first one times this L1, 0 plus f at the second one times this L1, 1. Okay? I'm just copying the theorem. It allows me to just write it straight out. What is f of x0? That's minus 2. What is L1, 0? That this guy here. That x minus x1 divided by 1 minus 3, like that. Plus the next point, which was 3, times this guy, which turns out to be x minus 1, and then we have 3 minus 1, and you're done. So as I promised, I would just write down the expression, and I would be done. Of course, it wouldn't kill you to simplify. And if you do this, it's 5 halves x minus not halves. But that's not the important part. And again, you shouldn't be impressed, but at least you see what's working. But now let's try to understand it. It's very easy to understand this. What happened here? I defined functions that are, it's actually easier to see with a quadratic, but let's start with this. I defined functions that are equal to 1 at one point and 0 at all the other ones. And I have all those functions. Now I take them. In this case, it's just 2. The one that was 0 that was equal to 1 at point 0, I multiply by f of x0. What is this? If you look at just this function, what property does it have? It's not equal to 1 at x0. It's equal to f of x0, right? Because I multiplied by that. What is it at all the other points? Still 0. So this term here has the property that it's equal to f of x0 at the first point, and it's 0 at all the other points. How about this guy? Same thing, of course, right? It's equal to f of x1 at point x1 and 0 at all the other ones. What happens if you add them? Well, these were 0 at all the other points. So at x1, this whole expression is going to be f of x1. This guy was 0 at the first point. So the whole expression is going to be of x0. Do you all see that this function must be equal to f of x0 at x0 and f of x1 at x1 because of that argument? Just because of the way these are constructed, being 1, 0, 0, 1. That's the key to this argument. You create these little nice L's, and when you're done with that, you just multiply and add. Now, why is that the right line that we want? that really the line we want? You need the argument of saying that it is still a straight line, a degree 1 polynomial, because I added 2 degree 1 polynomials. Okay? So it's just a degree 1 polynomial. And if it goes through the line, as we said before, that's only one line. So that's going to do it. Let me go one more factor, or one more degree. Now it's getting a little messy, but it's worth doing. So let's do the quadratic ones. So the quadratic ones would look like this. You would have to give me 3 points, and I'm going to put them in a non-obvious way. So n is equal to 2 means that you have n plus 1 equals 3 points. You're going to give me, I'm not going to interpolate anything right now. I'm just going to tell you that here's a 1, and you have to create the L's. The L's are defined. There are going to be 3 L's, L2, 0, L2, 1, L2, 2, right? They have the property, L2, 0 has the property that it's 1 at point 0 and 0 at all the other ones. And it's a quadratic polynomial. So you can draw that, and it's going to look like this. Right? This is L of 0 of 2, 0. And as I promised, I'm going to just write down what it is. I don't even need the numbers. Remember, if I gave you this problem, you couldn't, with your equation method that I raised, you couldn't even figure it out. You need numbers to solve your equation, unless you have a fancy computer. Here, it's a direct expression. I can just write down what it is. Even if I don't know the numbers x0, x1, I can keep the algebra, keep them symbolic. Anyway, let's just do it. How many factors are there now in the product? There's going to be 2, because I can be 0, 1, or 2, but we're going to skip one of them in each, right? So in the first one, we're skipping 0, which means that I is going to be 1 and 2. So you get x minus x1, x minus x2, divided by x0 minus x1, x0 minus x2. And if these were numbers, all this would just come out to a nice polynomial. It's a nice polynomial. Want to do one more? What is L of 2, 1? It agrees it's equal to 1 here, right? And 0 at all the other ones. So it has to look like this. And the expression is L of 2, 1 equals, very similar. Now you're skipping the 1. So you're getting these guys. And when you've done this a few times, you'll get very used to writing these expressions. You'll just see the pattern, and you won't really look at the formula after a while, because it's pretty obvious what I'm doing. So it is really as nice as I said. And then, of course, there's one more that I'm not going to write up. But we'll come to them later when we do an example. But you can now see that it's kind of getting nice, because now I could really just, I've written down 2 of them. If I write down the last one, which is obvious, and you give me 3 values, just like this example, let's say you add a 3rd point here. I just write them all out and multiply by f, and I'm done. So it certainly beats the equation problem in many cases. We'll go down to proving this after a while. Of course, we want to say something about the error. Completely analogous with Taylor. I know you didn't like Taylor. Many people expressed their concerns about this xi number and the fact that it depends on x and how do we bound it, et cetera, et cetera. And bad news is that it's going to be, the good news is that it's the same now, but if you didn't like it then, you won't like it now either. It's really, we're going to derive this formula by using Taylor. And it's just a different xi, but it's, I want you to see the parallels. When we did the Taylor, you had an error bound that had the form n plus first derivative of f at some xi divided by n plus 1 factorial. It's identical, right? Except that the xi's are different. Taylor didn't look like this, though. What did Taylor look like? It was really just x to the n plus 1. Or maybe x minus x0 if x0 wasn't 0, if it was general, right? So that's easy to remember. Let's see what it's saying. You're taking f of x. You're interpolating by one of these interpolating polynomials, like this guy here, for example. And the way I wrote it here is, of course, another way to say that this big expression here, after the px, is the error, right? It is the error. It's just that you can't evaluate it, so you're going to have to use it to bound the Again, if the context here, the technical part are what they are, but if the context is weird, just mirror it with Taylor, and you'll see exactly how it matches then. The big difference is that instead of x minus x0 to the n plus 1, there are now x minus x0 times x minus x1, etc., right? And from a practical problem point of view, I'll show you a little example on it. It just means that you get to bound it a little bit differently. In fact, these bounds turn out to be better in general. And I think it's fair to say I did erase my e to the x, but when I did my e to the x, I said maybe it's a better idea to do interpolating through three points than Taylor. And indeed, this expression can be used to say, yeah, it is better, because this expression here can be quite small. Remember, you want this to be small. It's an error. So let me just skip Neville for now and do that example, because that's, I think, a good priority. Let's skip that. It's kind of in the way, isn't it? Or maybe it's not. All right, here's my example. F of x is sine of pi x f. Okay? And x are going to be between 0 and 2. And the xi are 0, 1, and 2. Okay, that's not a very formal way to write it. Anyway, you guys wonder how am I going to do the exam problems? Well, this is how I'll do it. I'll pick functions and numbers that are so easy that when you plug in 0, 1, and 2, you get out 0, 1, and 0, right? I mean, this is the type of tricks. It's really hard to write a good exam problem. In a way, I wish I could let you have a calculator, but then it would cause a lot of other issues. Namely, it will test your skills on storing a lot of stuff in your calculator and stuff like that. So I can come up with a bunch of good problems like this. But anyway, if you wonder, just look at my Blackboard problems, because these I can do all by hand. Let's first just find the interpolating polynomial. Or maybe before you start, you want to make a sketch. So it seems like I'm having a function that looks like that. Right? 0, 1, 2. It seems like I'm saying, hey, sine is a complicated function. This is what I'm going to do. I'm going to take those 3 points, and I'm instead going to put a parabola through them. I'm not sure I drew this, right? It actually looks really nice, but they're not perfect, of course. Sine is not a parabola. But it looks like the problem statement has some potential for kind of accurate, right? Being reasonably close. So let's first just find the polynomial. You could do this using your linear equation method, but let's just use my new technique to show how easy it is. L of 2, 0. And from now on, we will often skip the 2 comma. Why? Because when you focus on a certain n, like here n was equal to 2, you see it's always L2 comma. So it could be understood from the context that it's just L0, L1, and L2. Okay? It's just when you talk about general n and everything. But let me do it now, but then I might get tired of it after a while. And I might skip the x, the parenthesis x as well. Okay, so it's very easy. You'll see the pattern. You have 3 points, 0, 1, and 2. Okay? The 0th one, you skip the first point, and you list all the other ones with x's minus. Okay? You can do that. Then you do it again, replacing the x by the point you skipped. Very nice. This is a half of x minus 1, x minus 2. So that's a polynomial that you, of course, when you do this, if you're ever uncertain, plug in 0 and make sure that this function is equal to L of 2, 0 is supposed to be equal to 1 at point 0. So plug in 0, and it should be equal to 1, and indeed it is. Plug in 1, and it should be 0. Plug in 2, and it should be 0. Keep on going. Same pattern. Now you ignore point the x equals 1, right? And then you replace it by 1. That's it. Short and nice. You get minus x, x minus 2. And you can confirm that if you plug in 1, it should be equal to 1. But if you plug in 0 or 2, it should be equal to 0. And the last one, of course, you skip the last point. 2 minus 0 2 minus 1. These are nice because there are no negative signs. All right, I'm done. Well, not with the whole problem, but I've written down those L's. So now immediately I have my interpolating polynomial, right? Oh, actually, now that I sent that up there. So let's write down the polynomial first. Px equals, and I'll do it, normally you won't even write this line, but I'm trying to be clear here. It's going to be f of 0 times L2, 0 plus f at 1, L of 2, 1 of x plus f of 2, L of 2, 2, x. Right? Of course, in the future, we'll just write it out. And you see why my case is super simple? Because it's 0 at the first and the last, so it turns out to be actually just equal to 1 times L1, which is minus x minus 2. So, you know, here's the expression. That is the guy I tried to draw up there, the interpolating polynomial. It just happened to be L1. A little too easy, maybe. The next step is usually you come to your boss and say, look, trust me, you can use this instead of sign between 0 and 1. You can replace this function by this easier expression. And it's not perfect, but I can guarantee you that it will never be off by more than. And you have to tell that, right? So that's how the typical setting is here, that you need to bound the error. So let's do it. And I don't have the slide here, but I'm going to repeat it again. What it said was that f of x minus your polynomial is equal to, actually let me take away because there are not supposed to be error bounds here. We'll put them back later. At some psi that depends on x over n plus 1 factorial. And then remember Taylor was x minus x0 to the power of n plus 1. But this guy instead does this product x minus x0, x minus x1, which we can write as product of x minus xi from 0 to n. Right? So in our case, it ends up being f3 of xi divided by 3 factorial times x minus x0, x minus x1, x minus x2. All right? So it's really what you got from Taylor, except that this is now looks a little bit different. And by the way, I should plug in 0 in all of those numbers. All right, let's look at this expression. f3 of x is what was x? Well, each time you differentiate, you pop out the pi half, right? So there's certainly going to be a pi half cube here. And then you know the deal with sine. It turns into cos, then it turns into minus sine, then it turns into minus cos, right? So it sounds like I'm going to have a minus cos pi x half. All right, and now comes the bounding game that you don't like. Bound it. Bound the error. F of x minus p of x. And now we'd like to put an absolute value. Well, can you do something sensible about this? X certainly can only take on values between 0 and 2. That might help you. But actually not, because this term is equal to 1 when it's 0. I'm not going to try to be too smart here because it's difficult. You don't know much about this xi. So all I'm going to say is that this is 1 at most in absolute. That's similar to what you did in your example. But of course, you have your pi half cubes here, right? So I'm going to put the pi half cubes here. So that's kind of easy in a way, because you don't know much. There are not many tricks you can do. If you plug in the numbers here, you're getting x, x minus 1, x minus 2. And you know what we would have done back in chapter 1? We would have said, hey, x is between 0 and 2. Let's just take them one by one. This can be at worst 2. this can actually be at worst 1, right? This could be, if x is equal to 0, this can be at worst 2. So one thing you could say is that this whole function is always less than 4 between 0 and 2. And that's correct. Turns out that, as I mentioned before, those bounds are usually good for Taylor, but they're really pessimistic here. This function is your magnitude away from what this function is. Because when you plug in 0 here, this guy will actually make it 0. So saying that this guy, it's actually a very small function. So let's be a little bit more ambitious. Let's just look at this function. And now this is just a Math 1A exercise, but let's do it anyway. So you want to maximize that function. And it's nothing else but finding the largest possible value for a function. OK? So maximize g of x, I just made that name up, equals x. What is the largest value for this function? How do you do it? It's equal to 0 at the edges, right? So why not just look at the derivatives? That's all we have to do. G prime of x. I'll do it a little quickly here because I think it's something like this. You set that to 0. These 2 points that are 1 plus minus 1 over square root of 3, OK? So you find the derivatives. What do you do with the derivatives? They are stationary point. You check the function at those values. So g of 1 plus 1 over square root of 3 turns out to be, don't worry about it, minus 2 square root of 3, 9. I just evaluated it. But it's actually something more like 385. It's a magnitude better than the 4 I came up with without thinking too much. And when you plug in this guy, it's similarly plus, I think, which is, of course, plus 0.385. What does that mean? Well, that means that this, based on what we just did, is less than or equal to pi half cubes times. Oh, I forgot the 1/6. Sorry. I forgot to divide by that. OK, but now comes my estimate for g. I just proved over there that g of x is never greater than that number. So let's plug it in here. 2 square root of 3 over 9, which turns out to be 0.25. All right? You see that if I had used the number 4 to bound that polynomial, it would have been 10 times larger, and I would say the error is 2.5. Do you think that would have been a good estimate for this case? Remember, the function looked like this. The function looked like this. It goes from 0 to 1, and I'm approximating by a function that does the same, right? And then I'm telling you the error could be, suppose I said 2.5. That's more than 100% error. That's just complete garbage. Here's a function that is equally good, right? I mean, it's just, there's no value in that. This, at least, tells you that you're never, actually, it's surprisingly high because it looks much better. This is still just over a somewhat pessimistic bound. But at least it's 1/4 of the interval, right, on the height direction. So it's a decent, it tells you that it doesn't go too far away. But, you know, it was certainly worthwhile doing this extra work to get a decent estimate on that number. But this is the game we play. Anyway, yeah, that's all I think. See you in office hours. Now, if you want to bug the 110B students, otherwise tomorrow.